Hi, pre-calc students. This is Unit 8, Day 2. Today we're going to be talking about how we can take some of our information and initial knowledge of trigonometry and start thinking about converting what we know about numbers in a plus bi form. It's been a little while since we talked about complex numbers. We're going to be taking these and converting them into what's called polar form. So right away at the top, you can see that a plus bi is defined as being in rectangular form. We'll talk about what that looks like in polar form in just a few moments. But first, in order to do that, we need to be able to define and graph complex numbers. So in a moment, you'll see that we're going to be graphing some, and it says we can graph complex numbers in it's not the xy plane anymore, it's going to be called the complex plane, which is a little strange because this looks like the x-axis and this looks like the y-axis, but we have to define the axes in a different way. It's called the complex plane when we graph complex numbers. And the way we're going to do this is we're going to use vectors, which may be a topic that you're familiar with and something that you've seen before, but if not, that's okay. So a vector, if you remember the movie Despicable Me, is something that has magnitude and direction. So magnitude is a length. Direction, of course, is just where it's headed. So when we define our axes in the complex plane, we're going to have the x-axis be the a-axis, a being the real numbers, and then the imaginary axis, or I'll call this the bi axis, is the one that's vertical. So when we graph something like 3 plus I, the 3 indicates that we're going 3 to the right. So the direction that we're heading is, of course, dependent on if that's positive or negative. When you have a plus I afterwards, that means you're going to go up 1 on the imaginary axis. And if you plot kind of a little point where it looks like the point 3, 1 would be, that's fine just to get started. But the complex number 3 plus I doesn't necessarily just correspond with that point in where we would consider the xy plane. The 3 plus I is actually this vector right here from the origin drawn to that point that we probably would think of as being 3, 1. So just a few quick notes. A vector has a starting point, and then at the end of the vector, you're going to see an arrow, which does not indicate that it goes on forever. That just indicates the direction that we're headed in. So again, this vector has a very specific length. We can find it using Pythagorean theorem if we wanted to, but when we talk about vectors with the arrow at the end, it doesn't mean that it's going in this direction forever and ever. So what about something like -2? Well, -2 might seem a little strange, but you can write it as plus 0i afterwards if you want, just to help make some sense of it. So to graph -2, we would go to the left 2 on the real number axis, and then just don't go up or down at all. So if I'm just going to kind of go to the left 2 in that direction, here's the vector -2 in the complex plane. And once you get the hang of it, graphing, although it sounds strange at first, is actually not so bad. -2 plus 4i, what would that look like? Well, if I go to the left 2 and then up 1, 2, 3, 4, you can plot the point that kind of corresponds with where -2, 4 is located. But then after that, from the origin, connect a vector to that location and put a little arrow at the end. Okay. So hopefully that's pretty solid for you at this point. If you want to try -3i, go for it. You can hit pause quick, but otherwise I'll show you really quickly what -3i looks like. Remember, the bi axis is the one that's vertical here. So -3i, if you count down 3 and just draw a vector from the origin, there is no real number component to this. Again, you can think of it as 0 minus 3i if you'd like, but you're not going left or right at all. It's just straight down 3 units there. So once we know how to graph these rectangular form numbers, these complex numbers, that will help us later on when we then start thinking about what it means to be in polar form. So if we take a look at polar form, we're going to derive what a number in a plus bi form looks like in a whole new way. And what I want you to think about is, let's draw a vector in the first quadrant here that represents some a plus bi number. So again, draw a vector that kind of just points to the outside of the circle somewhere. And you can see there's two things we're going to develop here. We're going to develop what r equals and what theta equals. So r is going to be this length of the vector right here. And then theta is going to be the angle formed with the x-axis. So we can actually list those things. That r is the length of the radius of this particular circle. And then theta is the angle formed with the x-axis. Now, in terms of that radius, by the way, I'm going to put something else in parentheses here, that if you were to then take that vector and wherever it hits the circle, kind of drop a line straight down to the x-axis, or what used to be the x-axis. Remember, this is the a-axis, this is now the b-I axis. What I want you to do is think about that when I drop that line straight down to this real number axis, that we've created a right triangle. So r is really the length of the hypotenuse of that right triangle. And that will help later on when we start doing some conversions between these two forms. What we have in polar form is where we're headed, and then this is called rectangular or just complex number form. Okay, so if I take a look at this triangle, I could actually label that this is a distance across of A. And then I went up on the imaginary axis B units. So if you want to label two sides of the triangle, that to the right was A and then up was B, that would be useful to do what we're going to do. By the way, I didn't even mention this, that I totally cheated and I used a compass. Remember those things from geometry to draw this really nice circle? So if your circle is a little more wobbly, no big deal. The right triangle relationships I want you to look at here are two important ones, one of them being cosine of theta. So if I asked you to find cosine of theta, you would look at this picture and do adjacent over the hypotenuse. So the adjacent side is what's labeled as A, and the hypotenuse is labeled as R. So once we have this relationship, what I want you to do is start thinking about, we're going to replace the A and the B in this formula with some trig relationships that we're establishing right here. So what I want you to do is think about how would you get A alone? And I'm pretty sure pretty quickly you could tell me that if you multiply both sides by R, A would equal R cos theta. Very similarly, if we think about what sine theta equals in this picture, sine of theta would be opposite over hypotenuse. That would equal B over R. Similarly, if you want to get B alone by multiplying both sides by R, B would equal R sine theta. So what we're really building towards here is we now have a definition for what A and B are equal to. Remember, A and B are the components of this complex number that was graphed up here. So if we have something in A plus BI form, what that really means is that we can replace A with the relationship R times cosine of theta. And similarly, we can replace B with R sine theta, and that's attached to the I. Now remember that R and theta are in our picture up here. R is the length of this hypotenuse, or the radius of the circle. Theta is the angle formed with the x-axis there. So if I have some information about R and theta, I can actually then work towards getting an A plus BI number from that. Now we're actually going to clean this up a little bit. So when I say clean this up, I mean that both of them have R in common. So you can factor out R as a GCF. So let's go ahead and do that. Take out the R. And then we get cos theta plus, typically in this new form that we're going to talk about, the I would be in front of sine theta, so we kind of don't lose it. So that's going to be I times sine theta. And this right here is known as polar form of a complex number. And that's what it says right here. Polar form is what we're working towards. This is the polar form of a complex number that started off as A plus BI. Now, it's going to seem a little strange, like what was the problem with A plus BI? Like, why do we even want this polar form? And that will become very apparent as we do more and more practice throughout this unit. So let's actually go to the next page on page 7. And on page 7, you'll see that we have just at the top, we're going to start practice converting between these two forms. But just to kind of formalize what we had at the bottom of page 6 there, when we're in rectangular form, that's the form that we were probably familiar with at the start of today, which was A plus BI. That's rectangular. Whereas polar form is our new form. It's R parentheses cosine theta plus I sine theta. And what I want us to be able to do is take something that's in this polar form and kind of work backwards and get us to A plus BI form. And there's a couple different ways we can do that. So you'll see down below the two methods that we're going to see today are both graphically and algebraically, and eventually I will just focus on one of those two things. This way we can make our process pretty easy. Okay, let's talk about this first example, 12 cos 30 plus I sine 30. So the graphical way to do this is by considering the following. If you were to sketch an angle of 30 degrees, which we have practiced with on day one, 30 degrees would definitely be an angle that's in quadrant 1. So what I want you to do is draw a triangle in the first quadrant and label the angle there as 30 degrees. Now remember the number out front, which is the value r. Where does r go? Well, from a second ago, r was the length of the hypotenuse. So we're going to put 12 on the hypotenuse of this triangle. And what we're trying to figure out is what is the horizontal piece here and what is the vertical piece? Because remember, if this is A and this is B, if I can find those two things, I can put this in A plus BI form. Well, luckily, we have some patterns that we established on day one for special right triangles. So if you need to look back at the day one notes, or if you want to take a look at this lovely whiteboard that I've written them on here, maybe I'll toss this under the dot cam every now and then. Special right triangles, one of them being the 30, 60, 90, which is the example we're looking at right now. So if the hypotenuse is 12, I want you to think about how I would label these two sides. And then similarly, we also have the 45, 45 triangle, which looks like this. So if you want to copy these down, maybe somewhere on your page, I'll leave that up to you. Or if you want to have them on a reference sheet, that's totally fine. So here are the ratio for the sides in the 45, 45, 90. And then this is what it looks like for the 30, 60, 90. So let's go ahead and actually apply that ratio to the picture that we have right here. If we have a 30, 60, 90, where across from the hypotenuse is 12, then across from 30 is half of that, which is 6. And if this is 60 up here, across from that is 6 radical 3. So what I would do is say that in A plus BI form, the distance to the right is 6 radical 3. And since the vertical distance is up 6, I'm going to write plus 6i. And that took a number that was in polar form and converted it to rectangular form. Those are terms that you're just going to get used to hearing over and over again. Polar and rectangular. So that's the official answer. And then the algebraic way would just be actually going back to the original right here and replacing cosine of 30 with what it equals. So remember that if you have a 30, 60, 90 triangle like this, the simplest way to evaluate is by assuming the side across from 30, which is x, is a 1. So the sides would get labeled as 1 radical 3 and 2. Cosine of 30, therefore, is adjacent over hypotenuse. That's radical 3 over 2. Plus then it's I times the sine of 30. Well, sine of 30 opposite over hypotenuse is a half. So you could actually just use the 30, 60, 90 with this simplest case of x equaling 1, and then distribute the 12 into those two terms. So you would get 12 radical 3 over 2 plus, when I do half of 12, that's just what, 6i at the end there? And then, of course, if you take half of 12 in that first term, you do get the same thing, 6 radical 3 plus 6i. If I'm being honest, though, even though I showed you the algebraic way here, I definitely prefer the graphical method. This starts to look a little messier, in my opinion, when we do it the algebraic way. So what I'll actually do for the next two is just focus on the graphical method, because you don't have to know two ways. But for those of you that really like this first way and you want to try it algebraically for the other two, you can confirm that we're getting the same results. Let's go ahead and try 10 cos 270 plus I sine 270. First step is to sketch the angle. So the angle of 270, this one's a little unique in that 270 is called quadrantal. It stops right on the borderline between quadrants 3 and 4. So if you were to draw the vector that represents that complex number, oh, by the way, the vector up here was just this vector right here, right, where the hypotenuse is. Here's the vector that represents that complex number. And then from there, this length right here of 10, that's the magnitude of that vector. That's the r value. So it's not always the hypotenuse of the triangle. In this case, it's just that distance going straight down. So remember, if I want to write this in A plus BI form, A is the distance left or right, BI is the distance up or down. We're going straight down, so we don't have any left-right component. There's no A. if you're going down 10, the answer would be either 0 minus 10i, or more likely you would just see me write negative 10i is the answer there. So 10 cos 270 plus I sine 270 is equivalent to negative 10i. Algebraically, we can get there the same way. Let's do the last one graphically too, because I hope you remember what pi is if you were to sketch it. 6 cos pi plus I sine pi. Okay, pi is an angle that actually is equivalent to 180, so it's halfway around. So here's the sketch of the angle. 6 is the distance that we are away from the origin. So if I draw a vector going straight to the left, this distance is 6. So remember, we've got our real axis, we've got the imaginary axis going up and down. This one goes left 6, but does not go up or down. So this one would just be negative 6 plus 0i. You got to account for that direction by putting negative 6 there. Or again, more commonly, you would just see me write negative 6. Okay, so those were 3 kind of quick practice questions, and we'll do maybe a couple more by the end of the lesson. But the last thing I want to show you before we get to more practice is that there is a shorthand version of writing 8 cos 0 plus I sine 0. So the r cos theta plus I sine theta. Typically, we'll abbreviate that. So I'll actually come back up here. We can abbreviate this in the form r cis theta. And this is an accepted abbreviation in all branches of mathematics. So if we abbreviate the inside as CIS, so cis would stand for cosine plus I sine, that might just be a shorthand version of writing this expanded form out every time. So for example, this first one would just be 8 cis 0. And 9 cos pi over 6 plus I sine pi over 6 is 9 cis pi over 6, same thing. Last one being 2 cis 7 pi over 6. So I'm sure you will really appreciate the fact that we have an abbreviated or shorthand version of this, because then the last thing we're going to do is you'll see some questions on page 8 that have that shorthand abbreviation, 5 cis 240. I will not write this for all the questions, but just to remind you, 5 cis 240, what that means, it's 5 parentheses cos 240 plus I sine 240. So now that we know that that's the longhand version of this, 240, where is that? Well, 240 is in quadrant 3. So there's my angle, sketch it. Okay, wherever the angle ends, you're going to create a triangle with the x-axis. This r value of 5 in r cis theta form is the hypotenuse. So put 5 on the hypotenuse. And the last thing, just like we had practice with on day 1, is what is this little reference angle on the inside here? Well, the reference angle would be 240, total angle, minus the 180, which is leaving you with 60 there. So this angle must be a 30. So now we just have to recall our 30, 60, 90 pattern, which we didn't use too long ago, but again, here it is for 30, 60, 90. If the hypotenuse is 5, we want to think about what goes across from 30 and what goes across from 60. So let's see, across from 30 would be half of 5. You can actually just leave that as 5 halves. If you want to put 2.5, that's okay. You'll never see me write decimals though. Across from 60 is that 5 halves number with a radical 3 attached. So those are those two side lengths. Now keep in mind, we're going to the left and then we're going down. So in a plus bi form, left is negative, so is down. Your final answer in rectangular form is negative 5 halves minus 5 halves I radical 3. So remember, the vertical piece always has the I attached to it, and for direction purposes, we need them both to be negative to get us to quadrant 3. Okay, let's just do one more. Let's do 40 cis 3 pi over 4. We'll save this one for class the next day. So when the angle's given in radians, it's really not that big of a deal. Hopefully you're pretty good at sketching radians by now. So let's see, 3 pi over 4. If I think about halfway being pi, that's really 4 pi over 4. And if this is 0, 2 pi over 4 would be a quarter of a circle. So 3 pi over 4 is right in quadrant 2. It's midway in between the quadrant border lines here. which means this reference angle is pi over 4. And if you want to convert to degrees, that's fine, but like that would be a 45-degree reference, or pi over 4 would be in there. So however you get to that point, we're now going to label that this is a length of 40. The only trick to this question in particular is that if that length is 40, usually in a 45-45 triangle, that length has a radical 2 attached to it. So if it doesn't have a radical 2, what will happen is that the other legs will both have radical 2's, and the length here will be half the hypotenuse. So I know that was kind of a lot of things that I said there, but I want you to label these legs as 20 radical 2 and 20 radical 2. So if there's no radical 2 here, put it on the legs and cut the hypotenuse in half. That's just kind of a good pattern to remember. But think of it this way. If you take this number and multiply by radical 2, that has to be the hypotenuse. 20 radical 2 is equivalent to 40. Oh, and by the way, we're going left, so we better label this one as negative. Going up is positive. In a plus bi form, this is negative 20 radical 2 plus 20I radical 2. And I know that sometimes these patterns take a little bit of practice to get used to with the 30, 60, 90, 45, 45, 90. But once we will do plenty of practice with this unit. Like you'll be pros at this, I promise, by the time we're done with Unit 8. So again, we'll skip number 3 for now. We'll work on that tomorrow. But if you have any questions, check in with me in class. Have a great rest of your day.